So we are back for the second part of this session on called post-selection inference valid double dipping. And so it's my pleasure to introduce Antoine Villié, who is a PhD student with Laurent Jacob in Lyon at LBBE, who is going to talk about something a bit different, because we are leaving the world of differential expression and methylation to go for something which can be applied to GWAS, genome-wide association studies, and which is a post-selection inference for sequence motifs. So Antoine, please go ahead.
Hey, so thanks a lot, Pierre, for the introduction and for giving me the opportunity to speak here today. And I'm very happy to present you the work we do with Philippe Weber and Laurent Jacob at the LBBE in Lyon about post-selection inference for sequence motifs. So indeed, this work takes place in the broader context of genome-wide association studies that are observational studies of genome-wide sets of genetic variants in different individuals to see if any variant is associated with a particular trait. And those studies are used in a lot of different fields, from genetic risk factor identification to plant breeding, for instance, by detecting the relationships between certain variants and the resistance to plant pathogens. So how does it work? Let's say we have n different persons with different phenotypes, either control or case, and a list of variants we can measure for every person. Then we can simply choose a variant, for instance, here the second one, and test the association according, for instance, to a linear model between this variant and the trait to figure out if this association is statistically significant or not. So now the question is, what are the variants that we consider to run our GWAS study? Standard approaches, for instance, for human GWAS, usually consider the single nucleotide polymorphisms as the variants, and also sometimes the list of short indels. And it seems to be an excellent choice, as those variants are able to capture the relevant genetic variations. But this may not be true anymore in some other cases, and for instance, for human tumors, where this translocation may occur, it's not the case anymore. And it is definitely not true anymore when we talk about the microbial genetic variations. A first reason for that is that SNPs and indels are only well defined over the core genome, that is, the genome containing gene families that are shared by all the organisms. Accessory genomes or variable genomes can be accounted for by gene presence or absence. But then what about non-coding regions? And what about SNPs that are located in accessory genomes? Okay, so moreover, SNPs and short indels are clearly not well suited for anything with no reference genome or everything that is hard to map. But by construction, GWAS studies are only able to detect significant associations between the phenotype and the variants that are in the variant list. And that is why it is crucial to have a list that covers all relevant genetic variants. So SNPs and indels are not well suited for microbial genetic variations. So how can we build variants that cover this issue? An initial approach relies on the use of K-Mers. So the K-Mers are the substrings of a given length K contained within a biological sequence. And here it can be noted that no reference genome or no alignment step are needed to identify those K-Mers. And so we can define our new variant list as the list of all the K-Mers of a given length and try to measure the association between the phenotype and the presence or absence pattern of each K-Mer in the sequences. And an asset of this is that it allows to capture many genetic variants, such as the SNPs, but also plasmids and other mobile genetic elements, and even translocations. But there are still drawbacks associated with those K-Mers. For instance, what if the best genetic determinant is a polymorphic sequence, like the one here? Then a single K-Mer presence or absence pattern cannot capture this polymorphic variant, and we will have strong dilution effects because we will need lots of K-Mers to represent this variant. And that's how we arrive to sequence motifs. So sequence motifs can be seen as a continuous generalization of the previous variants. And for instance, here on position 1, we can have either a T, an A, or a G. But on position 2, we'll always have an A, and on position 3, almost always a T, and in a few cases, I think it's a C. So therefore, sequence motifs are more expressive because there are less dilution effects, as we can capture those polymorphic sequences with only one motif. But another issue we now have is that the table here we usually used to run the GWAS study, this table now has an infinite number of lines, because sequence motifs live in a continuous space. Because indeed, if I change the weight associated with the letter T here on the first position, for instance, even with an infinitesimal change, I'll have a new sequence motif. So that's why we have an infinite list of variants. So we cannot test all of our variant lists, and we'll have to choose which motifs we want to test. But now we can't rely on the presence or absence pattern of the motif in the sequence because it makes no sense anymore. So we have to find a new way to fill in this table and to measure the trends of the motif within the sequence. Okay, so to quickly sum things up, we want to be able to run a GWAS-like procedure, but using sequence motifs as the variants. So to do so, we have to answer 3 questions. The first one is, how do we fill in the previous table? That is, how can we quantify the presence of a motif within a sequence? Then we just saw that this table now has an infinite number of lines and that we have to choose some of the motifs. So how do we select the most relevant ones in a certain way? And last but not least, how do we test those selected motifs? Because to build a well-calibrated test procedure, we have to take this selection in account, because if not, we will get over-optimistic p-values. So this is clearly a post-selection inference problem. Okay, so first question, we'll begin with first question. A way to measure the activation of the motif in a sequence is to use the function k here. So k depends on a sequence motif that we will denote z and a sequence x. And the sequence will be divided into K-Mers, denoted u here, of the same length as the motif z. Then the association can be defined by summing these exponentials, which depends on the Euclidean distance between the motifs and the K-Mers of the sequences and the bandwidth parameter sigma. So here, the K-Mers U and the motif Z are represented as position weight matrices. Here, it would have no sense to measure if a motif is equal to a K-Mer, as the motif is non-discrete. And that's why we use this formula to soften a Dirac distribution into a Gaussian one. So this function here is averaging on all the K-Mers of the sequence X, a soft measure of similarity between the K-Mers and a motif. And so you can see that the position of the K-Mer has no impact. And that's why we have here a translation invariance. Okay, so once this has been done, we can recreate the table here and almost run the GWAS study. But as we said, there exists a continuous infinity of sequence motifs. So we have just defined an infinite list of variants. And the question now is, how do we choose the variants that we want to test among this infinity? So we have to select some of them, the most relevant ones in a certain way. And once we have done this selection, we will have to take it into account for the test procedure. So, okay, we've just described the way to measure the activation of a sequence motif in a particular sequence thanks to this function K. And now we want to find a way to assess the association between the variants, that is to say, the activation of the motif and the phenotype. Okay, so the first way to do it is to choose the motif that maximizes the correlation between K of Z and X and the phenotype vector Y. Here we use the correlation squared because we want to maximize the absolute value of the correlation. Okay, so briefly, just a little aside here for those of you who are familiar with positive definite kernels. Here we stick with the framework described in kernel Psi paper from Slim et al. And here you can recognize the Halberschmidt independence criterion, which is a widely used criterion for kernel selection. And in our case, there exists a direct link between motif and kernel selection. Okay, so back to this objective function. An issue here is that this function is non-convex. So it might be a bit hard to optimize. And then another issue we have with this function is that when we apply this procedure, the information of a motif can be shared along several of the optimized motifs. For instance, here, we simulated data containing one true motif, the one here at the top. And when we applied the optimization procedure and let two optimized motifs enter the model, the information of the true motif was kind of splitted between the two output motifs. And this is an issue we want to avoid. So that's why, to solve this issue, we went from a joint optimization, where we optimize the set of several motifs at the same time, to a greedy approach where the motifs are optimized one at a time. It has several advantages, and in particular, it avoids, like I said, sharing the same information along several motifs, which was an issue we had before. So how does this greedy approach work? So at each step of the greedy algorithm, we select the motif that solves this equation here. This equation is very similar to the correlation we saw before, but we have added a projection matrix, the R here, to project the activation vector, K, as well as the phenotype vector onto the orthogonal complement of the previous activation vectors. So another way to see it is that we are maximizing the correlation between K and the residuals of Y with respect to the previous motifs. That is, for the first motif, we are maximizing the correlation squared, and for the following motifs, we are maximizing this correlation, but only in a subspace. Okay, and this procedure gives really satisfying results, and I'll show you some of them in a few seconds. But just before that, I'd like to give you a quick overview of the pending challenges. One of them is how do we fix the length of the motifs? Because here we want to be able to include motifs of different lengths in the selected model. So the first naive heuristic we have implemented is to solve this greedy algorithm at each step with motifs of growing length. For instance, starting to 5, then 6, 7, and so on, until the selected motif contains a position with an entropy greater than a threshold. Then we stop and we select this motif. But we are also working to analyze the variance that may enter the model when we add a new position to the motif to try to have a better length criteria than this naive one, but it's still a work in progress. Okay, so now let's have a quick look at the performances of our selection procedure. So the following test has been done by simulating 500 sequences of a fixed length. 2 true motifs were added in the data, and we are working here on a classification problem. That is, the negative sequences are completely random, and the positive ones have at least one K-Mer that is drawn from one of the 2 sequence motifs we have added. And for positive sequences, other positions are also completely random. Okay, so for instance here, the two true motifs included in the positive sequences are the two motifs at the top here. And we applied our selection procedure and let 4 optimized motifs enter the model. And here are the results. So we can see that the first motif and the second motif are very similar to the two true motifs. Why? And this is quite good. While the third and the fourth look like discretized version of these motifs and are not very satisfying. But that is okay because the real data only include the two motifs, and our model with two motifs is satisfying, so that's okay. And we obtain similar results when working with true motifs of different lengths. For instance, here, the first motif is much longer than the second. The first one has 22 positions and the second one only 16. But we still find the good motifs in first and second position. We still have the same issue for the third and the fourth, but it's not a problem. So we have also made tests to show that this procedure is also very robust to misclassification errors in the data. So there is an issue with the number of motifs entering the model. And in the previous test, we knew how many true motifs were included in the data. But for real case applications, we need a stopping rule to determine the number of motifs entering the model. So this is still a work in progress. And the first idea we have is to apply something like an elbow rule on the global score. But we are also working to try to control the false discovery rate or the family-wise error rate here. And those things raises the question of the statistical significance of the selected models. So how can we test those models? So just before going into the details of the inference, I would like to show you the link between sequence motif selection and the convolutional neural networks for biological sequences. Here, we will focus on the case of one hidden layer CNNs. So just a brief recap on how such networks work. So the aim of CNNs is to predict. They are prediction tools, and here they will predict the phenotype of an unannotated sequence. And to do so, the CNN will use several filters. Here it has a few different ones. And the first step is a convolution step, during which the input sequence will be scanned with windows of the same size than the filters, and scanning will be done thanks to a certain activation function. And here the windows are of length 3 on my sketch. Then the comparison between all the windows and a filter will produce a new vector, the pink one here. Then we'll have a pooling step where all the information of one filter is aggregated into a scala, for instance, by taking the mean. And finally, all those scalars are used during the prediction step to predict the phenotype associated with the input sequence. But what we see here is that if we choose our function k as the activation function for the CNN, and that we decide to go for average pooling, then we can write the objective function of this CNN like the objective here. So the CNN does not only solve the ridge regression here by finding the data that minimizes this part, but it also learns the filters to minimize this penalized loss. And in the previous equation, we know that beta has an analytical solution. And if we replace beta by its analytical solution, we can then rewrite the objective function of the CNN like the maximization of this new objective function. And this new objective function is quite close to the correlation one we had before, and there is just a normalization factor that is added in the CNN one. So finally, training a one hidden layer CNN is equivalent to the selection of some sequence motifs. So we can formally see the CNNs, which are prediction tools, as a way to select sequence motifs. And the procedure to select those motifs is the same than the one we have used before, but just with a slightly different objective function. but we can easily adapt our selection procedure to use this new objective function. Okay, so to sum things up on the selection procedure, we solved the question of the trends of a motif in a sequence by using this function k here. And then to choose a few relevant motifs, we saw that we can maximize an objective function, and this objective function can be the correlation one or something different to recreate the results from CNNs, or even something different if you want. But this objective function measures in some way the association between the motif and the phenotype. And to be the more general, we will name this objective function an association score, denoted S here, taking as inputs the motif and the phenotype. Another little aside, other methods already exist to select sequence motifs like streamer or drainer, and we will compare our selection procedure with those ones. Okay, so now the big question is, how do we test the selected motifs? So first, what exactly do we want to test? Because there are different models and different null hypotheses in the literature. And for instance, we can go for the one here. So let's consider the model Y, the phenotypes, equals to mu plus a Gaussian noise, sigma squared time epsilon. And here mu stands for the deterministic part of Y. So for a given set of motifs Z, a null hypothesis we can test is the statement that the association score between mu, the deterministic part, and Z is equal to 0. And so to say, we want to test, but the null hypothesis is there is no association between the motifs and the signal. To test this hypothesis, we can form the following statistic V, which is equal to the score of Z and Y, and study its distribution. But as we selected the motifs by picking the ones that maximize this score, we have to take this selection procedure into account, because otherwise the test would lead to over-optimistic p-values. And here we could apply standard data splitting strategy, like the ones used in Streamer, for instance, but they are not well suited because the total number of samples is limited and results in a loss of a statistical power. Okay, so how do we account for the selection procedure? So let's denote YA, the true phenotype, or I don't know how to name it, the phenotype observed with the sequences X. Our selection procedure, our optimization procedure, leads to the selection of a set of motifs that maximizes the score, and we name it Z star. The selection event E is then the one written here. That is, it contains all the vectors Y, or the phenotypes Y, that would lead to the selection of the same set of motifs Z star than YA here. And then we want to study the distribution of V conditionally to the event that Y belongs to E. So for now, to our knowledge, all post-selection inference frameworks deal with feature selection over a finite set of features, whereas here the motifs are selected among a continuous infinity of motifs, so we cannot apply those frameworks directly. So to study this distribution, we have to sample phenotypes Y in the selection event E. And a first idea would be to perform a rejection sampling in R to the N. So if N is the number of samples, then the Y vector is in R to the N because it contains the N phenotypes associated with each individual. So we could randomly draw vectors Y in R to the N, keep only the ones that belong to E, and study the corresponding distribution of V. But that is not tractable because the set E is a null set in R to the N. and I'll try to show you why. So we have proved that the subset E, which is sketched in purple here, is included in a vectorial subspace in pink, in a vectorial subspace of R to the n, and that this subspace in pink has a strictly lower dimension than n. So if we draw random points in R to the n, we have no chance of falling into the pink area, and especially no chance of falling into the purple one. But as we were able to identify this pink subspace, we are now able to perform rejection sampling. We just have to draw the points directly in this subspace and not in R to the n anymore. Okay, but we still face an issue, which is the question, from which distribution must the phenotypes be drawn in this pink subspace before the rejection sampling? Because as the subspace is not independent from the YA, from the observed phenotype, we have to take this dependence into account to find the right distribution. And this is, we still have issues with this to determine the right distribution here. But we hope we will find the answer soon and get to satisfying results. Okay, so just to conclude, finally, there is also another issue before using this method for GOS studies. Because as we quantify the presence of a motif thanks to an average pooling, this method has issue when working with long sequences, because the information carried by a K-Mer might be over-diluted over the sequence. But this will still be usable for the problematics that are tackled today by the existing motif discovery methods and the CNNs. And for instance, we can speak about the identification of transcription factor binding sites. Okay, so thanks a lot for your attention, and I really like to thank Philippe Weber and Laurent Jacob, my supervisor. And if you have any question, then I'll be happy to answer. Thank you.
Thank you very much, Antoine, for this talk. And so we have like 3 minutes for questions. So there is a question by Sophie, actually 2 questions related to the definition of K of Z and X. Question 1, if the K-Mer U occurs twice in the sequence X, does it count twice in the sum over the K-Mer U's of X?
Yeah. Yes, and for now it will count twice. We don't yet. I'm sorry, yes.
And question 2 is, how do you compute the distance D of Z and U between the motif and the K-Mer?
Okay, so the distance is the distance between 2 matrices. If the square norm is a norm of matrix of Z minus the matrix of U. So U is a K-Mer, so it's a one-hot encoded matrix, and Z is a matrix of the same dimensions, but with the constraint that all the columns will sum to 1. It's a position-weight matrices, so all the scalars in the matrices are probabilities, and then we just compute the difference between the two matrices, the norm of the difference.
So a second question by Alexandre Blin. What is the ground truth used in the training of the CNN?
I'm sorry, I didn't understand the beginning of the question.
What is the truth you're using for training the convolutional network?
Okay, so here we are.
I guess that's here, yes.
I'm sorry, it's a vocabulary issue. I don't understand the beginning. What is
I guess that's the training. What is the training set, basically?
Oh, okay. The training set is the same than the training set we would use for our optimization procedure. Like what I show here is that so K of Z and X are the same in the 2 equations here. And so what I wanted to show you here is that solving a CNN on the same data set is equivalent than maximizing an objective function that is quite similar to the correlation one here. Is it clear now?
Yeah, I think so. I mean, we'll have to ask Antoine, but I think so. Yeah. Thanks a lot.